Second example, I'm going to make the bottom be a cubic. This cubic, we are going to be able to factor partially as a linear factor times the quadratic, but the quadratic is going to be irreducible again. I'm going to make it a simpler example for the bottom of the fraction, at least. In the end, the entire example is not simpler, but the bottom of the fraction, the quadratic part, I'm going to make simpler. And just like with this first problem, I'm going to give you a little bit of insight into how to make a problem where the technique I'm going to show you works by writing the factored form of the bottom first and expanding it. So let's say the factored form of the bottom turns out to be this, x minus 3 times x squared plus 4. So I'm pretending that that's, well, I'm going to construct the example to make the bottom of the fraction factor that way. So I now need to expand this out once again with FOIL. First times first is now x cubed. Outside times outside is plus 4x. Inside times inside is not a like term. It's minus 3x squared. Last times last is negative 3 times 4 is minus 12. Let's now make at the bottom of a fraction, a rational function, where once again we'll make the numerator be 1. And we'll go from highest power down to lowest power. That's more of a standard form. And now let's pretend that this is an integral that I give you. Would such an integral show up on the gateway? No. Would an integral like the last example show up on the gateway? No. No trig substitution on the gateway, and in fact, nothing where you have to use completing the square. But they do show up on homework, like the homework due Monday. They might show up on exam 1 in 17 days. I don't know for sure. They might. So you need to understand. However, if they do show up on exam 1, they're complicated enough that I'd probably give you some help. You know, this was a fairly complicated thing. I'd probably give some help. This one turns out to be similarly complicated. However, the very first step is something I want you to be able to do, even without a hint. And that is to try to factor the bottom. Now, in general, cubics can be very hard to factor. I mean, even quadratics can be very hard to factor, especially when they have complex roots. I mean, they are factorable in theory with complex numbers. Cubics can be even harder. I know what the answer is because I decided what it should be ahead of time. But what if you didn't know that? What you'd want to do is you'd want to graph the cubic, not the entire rational function. So that would be x cubed minus 3x squared plus 4x minus 12. I'm trying to look for the roots of this so that I can hopefully factor it. There's the graph. It looks like it only has one real root, and it looks like it's 3. Now, we know for sure that it is 3 because of what I did up here. However, you should realize that just because it looks like it has a root of 3 doesn't mean it does have a root of 3. Maybe the root is ever so slightly different from 3. Maybe it could even be an irrational number, which would make the problem way hard. You're hoping it's 3, but how do you verify it's 3? And also factor it at the same time. You can use long division again. Some people might be good enough that they could factor just by guessing. But I think most people would want to use long division. You're dividing x minus 3 into the cubic, x cubed minus 3x squared plus 4x minus 12. polynomial long division, ask yourself, what do I need to multiply x by, the highest power there, to get x cubed? It's x squared. Put the answer up there. Then take that x squared and multiply it times each term here and put the answer down there before subtracting. X squared times x is x cubed. X squared times -3 is -3x squared. Subtract. Turns out pretty nice. Both of these cancel. You're down to just linear factors, linear terms, I should say. Can I stop? No, this is not the remainder yet, because its degree is still the same as the degree of what I'm dividing by. I can still ask what I can multiply x by to get 4x. I got to multiply it by 4. Take the 4 times each thing, you get 4x minus 12, and now I subtract and I get 0. The remainder is 0, which does mean x minus 3 is a factor. And since x squared plus 4 is the quotient, that means I can say this is true. If you can factor this without bothering to do the long division, that's okay. But I think most people, it's probably best to use long division. Theoretically, it's possible that I also could have gotten an x term in here. So in other words, I might have had to factor this as x minus 3 times a trinomial instead of a binomial with an x term in there. And that would have been a lot harder to do without long division. Now, x squared plus 4 is irreducible over the real numbers. Its roots are plus or minus 2i, where I is the imaginary unit, square root of -1. You can't factor that anymore. If it had been x squared minus 4 instead of x squared plus 4, then it could have been factored more. X squared minus 4 factors as x minus 2 times x plus 2. So if that had been an x squared minus 4, you'd want to factor it more. And your partial fraction expansion would have 3 fractions, each with a linear denominator. However, it's not an x squared minus 4, it's an x squared plus 4. We can't factor it anymore, but we can use partial fractions. We can still write this as something over the first denominator, x minus 3, plus something over the second one, x squared plus 4, where I do not factor that second one. However, there is a price to pay, you might say. The numerator here can be a constant, but the numerator here, in general, cannot be just a constant. It's got to be some linear function of x, like bx plus c. When the bottom of the fraction is an irreducible quadratic, no real roots, you've got to allow for a term that involves the first power of x. But we still want to solve for a, b, and c. So what do? We multiply both sides of this by that common denominator there to get rid of all the fractions. Get complete cancellation on the left. And on the right, you get partial cancellation. If you multiply that first fraction right there by x minus 3 times x squared plus 4, the x minus 3's cancel, leaving you with an x squared plus 4. And if you multiply the second fraction by x minus 3 times x squared plus 4, the x squared plus 4's cancel, leaving you with the numerator bx plus c times x minus 3. And at this point, just like we talked about on Wednesday, there's 2 approaches you could take. You could expand all this out to get something times x squared plus something times x plus a constant equals 1 for all x, 1 plus 0x plus 0x squared The coefficient of x squared can be set to 0, the coefficient of x can be set to 0, and the constant term can be set to 1, giving you a system of 3 linear equations in the 3 unknowns a, b, and c. However, if you've solved such systems, you know they can be very time consuming to solve. Maybe you use matrix operations, row operations, reduced row echelon form. Some of you might know about that, some of you might not. It's a big pain unless you use technology. To some degree, there's no way to completely avoid pain. But if you use the second technique of picking particular numbers, it is a little quicker. In fact, I can solve it in about 5 minutes. One value of x that's good to pick is 3, right? Because that'll make that 0. However, there's no real number for x to pick to make that 0. So that makes it a little harder than the examples from Wednesday. But you should probably still pick something simple, like x equals 0, for example, would be simple. And would also have the benefit of making the b go away right there if I pick x to be 0. So I think x equals 3 is a good thing to pick. X equals 0 is another good thing to pick. And maybe x equals 1 to make, or x equals 4 actually is what I did in the previous class, to make 4 minus 3 equal to 1. I could also try 1. It doesn't matter. Excuse me. So let's start with 3. If x equals 3, then I get 1 equals 13a. Yep. 3 squared is 9, plus 4 is 13, plus 0. That term becomes 0. So a is 1/13. I have very quickly solved for a. Let's try x equals 0 next. Plug in 0 there. 0 squared plus 4 is 4. I get a 4a, but a is 1/13. So this becomes 4/13. Did you track what I said there? Plug in 0 right there. 0 squared plus 4 is 4. This is 4a, but a is 1/13. 4 times 1/13 is 4/13. The b term goes away. B times 0 is 0. We're still left with c, though, times -3. 0 minus 3. This would mean 1 minus 4/13 is 9/13 equals -3c. I subtracted 4/13 from both sides. And so c dividing both sides by -3 is -3/13. I found a and I found c without too much work. One thing left to find, and that's b. Pick some other value of x, like maybe 1 or maybe 4. 1 probably would have been a little simpler, but I picked 4 in the last class, so I'll pick 4 for you guys. You'll get a 16a right there. Right? Plug in x equals 4. 20a, excuse me. Sorry. 4 squared 16 plus 4 is 20. 20a, but a is 1/13, so that's 20/13. Right here, plug in 4, you'll get 4b plus c is -3/13. Plug in 4 here, you get 4 minus 3, which is 1. Solve for b. 20/13 minus 3/13 is 17/13. 1 minus 17/13 is -4/13. Divide everything by 4. B is going to be -1/13. If I've not made a mistake, those are A, B, and C, and I do believe those match the last class, and I did not make a mistake in the last class, so these are good. How can you check this? What if you're worried you made a mistake? One way to check it is plug them back up in here. and add the fractions by getting the common denominator of x minus 3 times x squared plus 4. And simplify, and you should get that. That's one way to check. Another way to check is with Mathematica. There's a built-in command called apart. Capital A, apart. Square brackets, put your fraction inside there. This will break it apart into partial fractions, and I will do it with the original function, unfactored in the bottom. It still works. Make sure your cursor's on that line somewhere and do a shift enter. And there it is, and that is confirming the answer that we got is correct. The 13s are put in the bottoms of the fractions, that's okay. A is 1/13. That matches the 1 and the 13 there and there. B is negative 1/13 and C is negative 3/13, matching the negative 1 in front of the x over 13 and the negative 3/13. So this is confirming that our answer is correct. We're not done, right? We still need to do the integral. We're not done with the pain either, with the trickiness. It's still tricky. Part of it's easy, part of it's tricky. That's the integral I'm trying to do. I want to use this partial fraction expansion as well with the values of A, B, and C that I found. So I'm going to do A over x minus 3 plus B times x, negative 1/13 x, plus C, which is minus 3/13, all over x squared plus 4. The first one here is easy to integrate. Right? That'll be 1/13 natural log of the absolute value of x minus 3. That one's not so easy though, but it's doable. It's very tricky though. Let's go ahead and do the first one, 1/13 natural log of the absolute value of x minus 3. And then let's write the integral of this one, except what you want to do to deal with the trickiness of it is you want to split this apart into two fractions, both with the same common denominator. And I'm going to do this with one integral symbol, but the techniques that I use for each fraction to integrate it is going to be different. Still an x squared plus 4 in the bottom for each one. This first one is going to have an x on top with some constant in front of it. The second one's going to have just a constant. In order to figure out how to do the integrals in each case, it's good to write those things, the negative 1/13 x and the negative 3/13, in certain special ways. What am I getting at? With the one that is going to have the x up top, what I'd like to imagine, listen really carefully here. What I'd like to imagine is integrating that by doing a substitution, w equals x squared plus 4. Why? Because if w is x squared plus 4, dw will be 2x dx. The point is dw will have an x in it, just like this term has an x in it. But it's a 2x, not a negative 1/13 x. So I need to kind of do some tricky manipulations here to get a 2x in there. Write negative 1/13 x as negative 1/13 times 1/2 times 2x. That's getting a 2x in there with a negative really 1/26 in front of it. But if I now let w equal x squared plus 4, dw is 2x dx. There's a 2x there now. And the negative 126 can just go out in the front. With this one, the negative 3/13 over that, constant over x squared plus 4, I hope intuitively it makes sense that the answer is going to involve inverse tangent, like our first example did. But there's a 4 there instead of a 1. How do you deal with that? You could factor it out. You could think of x squared plus 4 as 4 times, in parentheses, x squared over 4 plus 1, or if you prefer, what's better, x over 2 squared plus 1. And the 4 that's in front can be thought of as multiplication by 1/4, because it's in the bottom of the fraction. What about the top? It's this negative 3/13. Once again, we could imagine doing a substitution. This is tricky, even extra tricky. Imagine letting w equal x over 2. So that dw is 1/2 dx. So what I'm trying to hint at is you want to get a 1/2 in there somewhere. How? Think of negative 3/13 as negative 3/13 times 2 times 1/2, and that puts a 1/2 in there. So that in my mind, in my imagination, I'm doing it in my imagination. You might prefer doing it by hand on paper. I'm imagining letting w equal x over 2, and dw is then 1/2 dx, and I got a 1/2 dx there, so that will become dw. But then this thing is there as well. That becomes negative 6/13. I also still have the 4 there. So I still got to divide by 4 as well. Negative 6/52. 13 times 4 is 52. And negative 6/52 reduces to negative 3/26. I'm doing all this stuff in my head. You probably want to write it down when you're trying these kinds of problems. So the upshot of all this is the final answer is going to be 1/13 natural log of the absolute value of x minus 3 minus negative 1/13 times 1/2 is negative 1/26. Natural log, why natural log? Because I'm imagining doing w equals x squared plus 4. So dw is 2x dx, and I'm integrating 1/w. W is x squared plus 4. Do absolute value of x squared plus 4, which when x is real is never negative, so I actually don't need the absolute value signs, but it doesn't hurt to include them. And then the last one is the trickiest. Again, I've got negative 6/13 divided by 4. It's negative 6/52, which reduces to negative 3/26. Minus 3/26 inverse tangent of x over 2 plus c. If you are worried you've made a mistake, you can always double check it by differentiation. Certainly that one differentiates pretty simply to this. This one, when you differentiate it, imagine with me, you get 1/x squared plus 4 times 2x. And then 2 times negative 1/26 is negative 1/13. And with this one, when you differentiate it, ignoring the negative 3/26 for the moment, you get 1/1 plus x over 2 quantity squared, just like that. And the negative 3/26, it's tricky, can be written as negative 6/52, and the 52 can be written as 4 times 13. The 4 can be brought through the parentheses like this to get that. And the negative 3/13 can go up top, just like you see back over here. Maybe you're sleeping. Maybe you're zoning out. Maybe you're sort of following me, but you're like, okay, wait, I lost you there. Or maybe you're completely tracking with me. No matter which category you're in, you got to work on these things on your own, right? You can't just expect to get it right without working on it. What's most amazing to me is not getting an answer like this and just, okay, that's the answer. It's that it works at all, that you can find an answer at all. That's what's most amazing to me. It can be done. There's no intuition that that's going to be the answer ahead of time, unless you've got enough experience with this stuff to know it involves logs and inverse tangents. What this is hinting at is, in theory, you can always integrate any rational function, in theory. Ratios of polynomials, perhaps first by doing long division to get a quotient and remainder, then possibly doing partial fractions, factoring partial fractions, possibly doing same kind of stuff we're doing here. But if the degrees are really high, that could be really hard, or if maybe even you might say impossible in a practical sense. In theory, it's possible, just in practice, it's too hard. Do such integrals come up in applications? I have never seen a particular application of this particular integral in my life. There are applications I've seen plenty of times where you need to use partial fractions. We will see some when we talk about differential equations. Just never any quite this complicated. I'm not saying they don't exist. I'm just saying I haven't run across them myself. I make plenty of mistakes. I know this is right because I checked the answer with Mathematica. We'll check it again here. You know, a lot of you are engineering majors. You're going to run across really long, complicated problems in future years here. When you make mistakes, the key thing is you got to try to fix them. That's part of engineering, in fact, is fixing mistakes, right? Bridges that are defective or whatever. You got to fix things that people have done. So you got to figure out where the mistake is and how to fix it. So that takes time and effort. Maybe it's not always fixable, but there we go. We got a match. Again, Mathematica doesn't bother with the plus C. You notice Mathematica doesn't bother with the absolute value signs either. They assume you know to put them there. Again, this one's not absolutely necessary because x squared plus 4 is positive, but it doesn't hurt to put it there. Question? Yeah, that's the same as if I did absolute value signs. Absolute value of x minus 3 is the same as absolute value of 3 minus x. So, but thanks for pointing that out.